Welcome to Calculus BC. In today's episode, we're going to be discussing Chapter 9.3, which is the integral test. In order to understand the integral test, we have to first come to terms with the fact that we are going to be doing a lot of comparing between series and functions. As we've discussed many times before, the series and the function behave the same way, which is why we can often compare the two situations together. In order to make my first comparison, I'm going to go ahead and take a look at the integral from 1 to infinity of 1 over x squared dx. Now, using an improper integral, what I'm going to do is I'm going to say the limit as n goes to infinity, right? Because we're not just going to straight up plug in infinity. That doesn't really make a whole lot of sense. I'm going to call him 1 to n, and I'm going to call him x to the negative 2 dx. And I'm going to go ahead and integrate this idea here. So I'm going to go ahead and get negative x to the negative 1 on the interval from 1 to n, limit as n goes to infinity. And the way this works is I'm going to say this is the limit as n goes to infinity of, looks like negative, actually I'll put the negative all the way on the outside, and I'll go 1 over x on 1 to n. So now, all I have to do is effectively just evaluate this integral from upper bound minus lower bound. So that's going to be the negative limit as n goes to infinity of 1 over n minus 1 over 1. Well, if I take the limit as n goes to infinity, this whole expression goes to 0, and I'm left with just negative 1. But the negative from the outside of the limit pops in, and I end up getting 1. Back when we did improper integrals, we learned this to be called a convergent integral. And that is because when we took the improper integral as the x values of my limits of integration went to infinity, we actually got an actual number rather than something that just exploded into infinity and diverged. So the way this works graphically is if I was to draw a graph of this thing, and I was to do 1 over x squared, it would probably dip down like something that looks kind of like this. What I'd want to do is I'm going to go ahead and understand that the area that I'm getting, that I'm accumulating from this improper integral, is going to be a convergent integral. So I'm going to go and match this with its appropriate Riemann sum. And the way I'm going to do that is, in order for this thing to converge, this Riemann sum will have to be taken from a particular side. And so that, if I take my first height from 1, the only way I'm going to be able to stay underneath this curve, I could go to the right? But that would result in an overestimated Riemann sum. Instead, because I know this is convergent and I know my rectangles will all then have to be underneath the curve, I'm going to use a right-handed rule on this particular function right here. And again, that allows for the area to be underneath the curve, like literally underneath the curve without overlapping. And again, I'm doing this because I know that my improper integral is a convergent integral. So how does this relate to what this is? Well, if I do the summation from n equals 1 to infinity of 1 over n squared, well, I know this thing is going to converge, right? And so this thing will converge because its associated integral from 1 to infinity of 1 over x squared dx also converged. Now, if I was to actually draw this in, color this in, the sequence would actually be indicative of the white rectangles, because each sequence, right, remember sequences are generated by plugging in only positive whole numbers. So hopefully it makes sense that we're plugging in, a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. Now, notice how I'm leaving a bunch of space underneath the curve here, which is going to be underneath my integral's value. But if I was to look at the integral, what would happen is I would end up getting all of this space, all of this space, all of this space, along with all of this, along with all of this, and along with all of this. So each time my rectangle moved to the right, I'm accumulating so much more area underneath the curve based on these overlapping areas, right? Based on these spaces that are being left out. So because I can conclude that my summation is smaller than my area, right? We can actually write this as an inequality like this. My summation is smaller than my area. If this guy converges, then because he's larger, he will flatten out this guy, which will also converge. So hopefully that makes sense. I'm giving you guys a brief introduction to the integral test right now. I haven't quite answered a question using the integral test yet, and there are certain conditions that need to be met for this to be met, but this is just the introduction. Give me a second. I'll be right back with the next example. In this example, this is the integral from 1 to infinity of 1 over x dx. And if I was to go ahead and do him as an improper integral again, it would be the limit as n goes to infinity of the integral from 1 to n of 1 over x dx. And that's going to end up being, looks like the natural log of x on 1 to n, again, limit as n goes to infinity, which then becomes ln of n minus ln of 1. Again, limit as n goes to infinity here. ln of 1 is 0, but this guy clearly diverges. And when we first started doing improper integrals, I mentioned the notion that despite the fact that the terms are getting smaller and smaller, they're not getting small fast enough to make the sum of the terms converge. And so what's happening here is that you have a similar curve. It doesn't arc down quite as aggressively as the 1 over x squared. But now I'm going to go and call this 1, I'm going to call this 2, I'm going to call this 3, and 4, and 5. My first height does in fact come from 1, but instead of moving to the left now, which would create an underestimation, because my improper integral told me that I'd be diverging, that means that the area, that indicates that the area would be an overestimation, meaning I'd have to be using the left-handed rule so that I could be above my curve. And if I keep extending all of these areas above the curve, I'm going to end up with an infinite area that would just diverge into infinity. And so what we're going to do here is we're going to say, all right, the summation from n equals 1 to infinity of 1 over n, right, that is actually greater than the integral from 1 to x, 1 to infinity of 1 over x dx. And so because this guy diverges, by comparison or by use of an integral test, we can say this guy also diverges. And that is the introduction to the integral test right there. And that is to say that the way a function and the way a function's integral and the way its summation behave will always be the same. So if you can prove that an integral would converge, that means that its corresponding series would also converge. Likewise, if the integral diverged, you would then say that the corresponding that the corresponding series would diverge. So let's get that down. Okay, so the integral test reads, suppose f is a continuous, positive, decreasing function on 1 to infinity, and let a sub n equal f of n. Then the series from n equals 1 to infinity of a sub n is convergent if and only if the improper integral is convergent. So if you look at the conditions, if the integral converges, then the series converges. If the integral diverges, then the series converges. So we talked about that a few seconds ago, right? When we talked about how the integral of the function and the series summation would behave the same way. And so hopefully that makes enough sense. The idea that f needs to be continuous and positive, the continuous, hopefully that should make sense. But positive and decreasing, that actually should make sense too. Because if the function was increasing, then that means that the areas underneath would be getting larger and larger and larger, which means you would actually get to infinity without even questioning, or without even needing the integral test. The integral test ultimately determines whether or not a series is decreasing fast enough to create a convergent sum. So let's go and take a look at a couple of examples of this, that way we can solidify this idea here. So what I'm going to do is I'm going to start with example 1 here, and it's going to be the sum from n equals 1 to infinity of 1 over n squared plus 1. So what I'm going to do is I'm going to say on the side, let f of x equal 1 over x squared plus 1. And I'm going to say that f of x is continuous, positive, and decreasing on the interval from 1 to infinity. Now, this one here is something that I'm going to actually prove. So I'm going to go and say f prime of x is equal to, actually, you know what, I'm going to call him something real quick here. I'm going to call him x squared plus 1 to the negative 1 power. So I'm going to say this is negative x squared plus 1 to the negative 2 times 2x, which means I'm going to have negative 2x over x squared plus 1 squared. So it looks like my only critical number is going to be 0. So from here, critical value is going to be 0. So this guy's always positive. He goes from plus minus. So that means that we are, in fact, decreasing, right? So f is decreasing on, looks like 0 to infinity because f prime is negative. And therefore, f is decreasing on 1 to infinity. So now that these have been established, I'm going to go ahead and initiate the integral test on this thing. So I'm going to say, all right, the integral from 1 to infinity of 1 over x squared plus 1 dx. But I'm going to go and just take the limit as n goes to infinity and do an improper integral on it. Well, what does that get me? Oops, that should be an n right there. Whoops. That's going to get me tan inverse of x on the interval from 1 to n. Again, limit as n goes to infinity. And when I go to evaluate this integral now, so I'm going to get limit as n goes to infinity of tan inverse of n minus tan inverse of 1. Well, as tan inverse of n goes to infinity, I'm going to end up with pi over 2 because of my asymptote. And then tan inverse of 1 is negative pi over 4. So what I end up getting is I end up getting pi over 4. So the way I justify this now is I say the integral from 1 to infinity of 1 over x squared plus 1 dx converges, and therefore I have to identify what test I used. So therefore, by the integral test, the sum from n equals 1 to infinity of 1 over n squared plus 1 must also converge. And that's my justification right there. That's how I end up using the integral test in order to prove convergence. So hopefully that makes sense. I'll be right back with the next example. So before I move on to the next example, I do want to make sure that we are aware I received pi over 4 as my answer, but that doesn't mean that this is what the series converges to. The fact that I got a finite answer simply means that the series converges, but we don't know what it converges towards. And so again, we talked about this in the last class where in order for us to figure out what the sum actually is, we would need a partial sum for the nth partial sum. We don't have that this time, so the fact that we got a finite number only indicates convergence. Again, not what convergence towards. So make sure we're clear about that. So before we get into the next example, let's get into the next example. Okay, let's take a look at this problem here. The sum from n equals 1 to infinity of ln of n over n. So again, what is it? First of all, let's talk about what is it that's drawing me towards the integral test other than the fact that this is the integral test chapter. Well, what's drawing me towards the integral test here is that I'm looking at a function and I see its derivative being multiplied. In fact, I could probably rewrite this as 1 over n times ln of n. And so we know how to deal with situations like this where we have a function and its derivative present. We would compare it to this, ln of x over x, right? And so I'm going to go ahead and say f prime of x is equal to low d high minus high d low, square the bottom, and away we go. So I'm going to cancel those out. I get 1 minus ln of x over x squared. F prime of x equals that. Now, why did I do that? This is to show that the that the sequence is decreasing, right? And so from here, my only critical numbers are going to be 0 and e. X squared is always positive, so the 1 minus ln of x is going to go plus, plus, minus. Of course, he doesn't exist from behind here. So it looks like we are strictly decreasing from all x's greater than 3, right, or greater than or equal to 3. So we can say then that f of x is decreasing for all x greater than e. We know that f of x is positive and f of x is continuous. So the fact that x is decreasing for all x greater than e means that the sequence terms would be decreasing for all x being greater than or equal to 3. So hopefully that makes sense. You can actually just call it e right there. So let's go and take the integral of this thing. So I've got the integral from 1 to n of the limit as n goes to infinity. I'll go and say 1 over x times ln of x dx. It's a u sub, right? Because we see a function, we see its derivative. So I'll say u equals ln of x, du is equal to 1 over x dx. Here's my linkage. Again, it's an improper integral. I'll go and do an indefinite integral on the side here. That way we don't, cross thread our limits of integration. This will just become u du, which then becomes u squared plus c, or actually just u squared, right? I mean, we're going to do an improper integral anyway. So this becomes ln of x squared over 2. And so from here, oops, I forgot about that, divided by 2 right there. So now from here, that is all going to be underneath this guy, right? So this is really the limit as n goes to infinity of ln of x squared. And I'm going to go and call him from 1 to n. I'm going to kick the 1/2 on the outside there. And then if I let this limit happen, so 1/2 limit as n goes to infinity, I'll have ln of n squared minus ln of 1 squared. Of course, that guy's 0. This guy diverges. So my ultimate summation here is that I can say the integral from 1 to infinity of ln of x over x dx diverges. Therefore, by the integral test, the sum from n equals 1 to infinity of ln of n over n must also diverge. So hopefully that made enough sense to you. I'll be back with another example of another test, actually. So we'll be back with another test in just a second. Now that we have the integral test taken care of, let's go and take a look at what's called the p-series. And so we've seen this before, actually, in improper integrals. And it would look like this. From n equals 1 to infinity of 1 over n to the p. And the question is, what values of p will make the series converge? And some of you, I'm hoping, are kind of remembering what that was from improper integrals, but we will actually use the integral test to show this. So I'm going to go ahead and say, all right, let f of x equal 1 over x to the p. Well, I can say f of x is continuous, positive, and decreasing for all x greater than 1. And so now from here, let's go and do the limit as n goes to infinity of the integral from 1 to n of, I'll go and call them x to the negative p dx. And what that's going to get me is it's going to be the limit as n goes to infinity of, looks like x to the negative p plus 1 over negative p plus 1 on the interval from 1 to n. And now what I'm going to do is I'm going to go ahead and say, all right, this is the limit as n goes to infinity of, looks like n to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. So this guy, he's just a constant, so I don't really need to worry about him. But remember, I'm letting n go to negative infinity, or letting n go to infinity here, which means if this guy's going to converge, this part of the expression here will need to be moved to the bottom, right, in order for this entire fraction to become nothing, which would force the constant to stay there. And so the only way I can do that will be if that exponent is negative. And so that means that negative p plus 1 has got to be less than 0. In other words, if I add p to both sides, 1 would have to be less than p, or p would have to be greater than 1. And we have hopefully remembered this from improper integrals, because we used it sometimes when we were just trying to guess whether or not an improper integral would converge or diverge. So now this makes checking certain series pretty easy. If I said the integral from, not the integral, but the summation from 1 to infinity of 1 over n cubed, you wouldn't have to do the integral test on this anymore. You could just say convergent by p series. And you would say that p is equal to 3. Actually, another one you could do this on would be from n equals 1 to infinity of 1 over n. And then this would actually diverge by p series. And that's because p equaled 1, right? Now, actually, you can justify the divergence of this series like this. But this series right here actually has a particular name. It's actually called the harmonic series. And this harmonic series is known to diverge. And so this can be considered, assumed knowledge at this point. So if you just said this is a harmonic series, therefore diverges, that would be a perfectly acceptable answer. Something to kind of give you guys a little bit of a preview on before we close up shop here. If I start from n equals 1 to infinity of n cubed over n to the 4th plus 2, take a wild swing. Do you think this would diverge or do you think this would converge? And so if you took a second to think about it, this would definitely diverge. Because if you looked at it as a type of p series, p would equal 1 right here. But we're not going to use that as our justification here. In the next episode, we're going to talk about a type of test that will allow us to determine with certainty that this type of series would in fact diverge. But that's going to be for the next episode. That'll wrap things up for the integral and p series tests. So we've got 3 tests under our belt now. We've got the divergence test, or otherwise known as the nth term test. We have the integral test, and now we have the p series test. We're going to learn 2 more tests in the next episode. But as always, please leave comments or questions in the comments area. I will see you all in the next episode.